Good evening. It's my pleasure to introduce Josh Trzasko as tonight's speaker. Josh's interest in MRI began in high school following a severe concussion after a mountain biking accident, and he was wearing a helmet, for the record. But after that, he pursued his interest by going to Cornell, where he received a Bachelor's of Science degree in Electrical and Computer Engineering in 2003. And then he furthered his studies at Mayo Graduate School and received his Ph.D. in 2009. Since 2009, he's had a lot of pestering questions from me, and in 2014, he became an associate consultant in the Department of Radiology at Mayo Clinic and assistant professor of radiology and biomedical engineering at Mayo Graduate School. He's currently an IEEE senior member and a member of the Bioimaging and Signal Processing Technical Committee, which oversees the medical imaging component of all the journals and conferences. His current research focuses on developing and applying novel mathematical and computational, what is this? Here we go. Tools, there we go, for inverse problems in magnetic resonance imaging, including limited data reconstruction, artifact correction, and quantitative imaging. And today he's going to talk to us about some of those in his talk, Sparsity and Beyond, Modern Strategies for Magnetic Resonance Image Reconstruction.
Thank you, Eric. Then can we get, from up in the projector booth, can we get the lights down a little bit, kind of in presentation mode too? So while they're doing that, so yeah, thanks everybody for coming. I've been a member of IEEE for quite a long time now. I just told Paula this actually with my birthday recently marked actually being an IEEE member for a full half of my life. So that was somewhat sobering. But yeah, it's been great to be involved at kind of multiple levels, from the local level all the way up to the national level. It's a really great society. So today, as Eric mentioned, I'm going to be talking about magnetic resonance image reconstruction. And this is a fairly broad topic, so we're not going to attempt to cover everything here today. And we're going to essentially focus on applications of some modern sampling theorems, particularly a topic known as compressed sensing and high-dimensional generalizations of that, and how we can use those in magnetic resonance reconstruction, and particularly the task of taking the raw data that's collected by the scanner and solving the inverse problems used to estimate images from those. And we're going to walk through some of the kind of, what's actually involved in these, what are the practical challenges, and then how can we start to develop some of these theories, generalize them, and apply them to a number of outstanding problems, and show you exactly some cases where we're actually using this well over a dozen times every single day in the clinic here now. So just trying to show the full spectrum of going from theory all the way into practice for the application of these. So these are the basic topics that I'm going to be covering here. We're going to kind of outline why do we need this, why do we actually try to have speed in MRI? Why do we, what's the advantage of actually going fast? From here, I'm going to give you a quick crash course in MR reconstruction theory, tell you kind of the basic mathematics about what's going on here. And then we'll get into the kind of, nuts and bolts of sparsity and compressed sensing. Many of you have probably heard about this now. It's been around for about 10 years. I've been fortunate to get involved in this right from the very beginning, and I've worked with a lot of the kind of core signal processing theorists who developed this out at Stanford and whatnot. And we've been able to kind of blend a lot of the techniques and, again, going from theory to practice here and show you some of that. I'll show you a number of examples of how we actually use, again, these technologies in MR reconstruction, both that we've done here at Mayo as well as from a number of my collaborators at other institutions. And then we'll get into kind of what are some of the hot topics nowadays that people are focusing on. And then from there, jump into what has been kind of a main component of my research in the past couple of years, whereas generalizing these notions to a lot higher dimensional problems, going from simple kind of, classic linear vector signal problem, vector signal processing problems up to matrices and tensor regression, and how to extend these notions of sparsity to higher dimensional spaces and leverage them and actually solve these problems in an efficient manner. So to kind of preface this to get started, hopefully that'll go away again in a second. Magnetic resonance imaging, for those of you not familiar with it, is a non-invasive modality for imaging materials in the human body, and unlike other X-ray based techniques, these does not use any ionizing radiation, so there's no inherent harm from the radiation that's used here. Now, one of the reasons that MRI is used so much clinically nowadays, and it's really celebrated there, is it's incredibly flexible. We can do lots of things ranging from arbitrary orientation imaging. You can look at three-dimensional volumes from all different angles as well as from oblique orientations. You can vary your contrast level significantly to highlight different types of anatomy. And hopefully you can see from some of these examples over here where we can make certain parts around the knee over here really pop out in terms of the cartilage and whatnot. You can tune these to different chemical species, although MR is typically geared towards protons, which comprise water, which makes up most of your body. You can tailor this to other things like fat or phosphorus or other materials as well. So it's, again, very flexible. And one of the other really more recent advantages is that you can not only look at anatomy, but you can start to look at function. And you can, the classic example of this is in functional MRI, where you look at local oxygen levels and how those change during things like thought to figure out areas of activation. But you can also look at things about how contrast flows through your vessels, and it might get stuck in areas of stenosis or blockage. You can start to look at things about where water diffuses locally. You can actually start to look at mechanical properties and study things like, what different tissues or parts of tissues are stiff in some areas versus the others, like in the liver over here. Or we can look at how blood perfuses, for example, following a stroke in the brain. So again, lots and lots and lots of different options here, and we can't possibly cover all of these now. So we'll just focus on a couple of different cases. So how does MRI work? So here's kind of a quick crash course in 4 steps about how MR works. There's obviously a lot more going on under the hood. But the way to think about this in a typical MR experiment, and what I'm going to try to differentiate here, is it operates very differently from a digital camera. We all know a digital camera, you open up your shutter, there's a sensor that collects all your pixels all at once, turn it off, you get all your samples. In that case, if you really want to get a higher resolution image, you essentially add more pixels inside your sensor. MR works very differently. What happens is we place an object of interest inside a strong magnetic field. Most of you have seen an MR scanner here, so the object, in this case the human, is going inside the bore here. And then what happens here is all the protons either align parallel or anti-parallel with the main magnetic field which runs through the bore here. At this point, we're going to apply radio frequency waves in a very controlled manner, and these are going to perturb these spins that are inside your body. And then once we've removed those radio frequency waves, different spins associated with different tissues are going to respond, go back essentially into equilibrium at different rates. And we're going to measure those, and we're going to essentially measure those different rates, and that's what's going to allow us to actually discriminate where different tissues are in different parts of the body. Now, what we need to do is, again, I'm saying this is different than a digital camera, we have to essentially repeat this process for all these different frequencies that we're measuring. Just like you might tune a radio to different frequencies, we essentially have to tune to all these different frequencies that might occur during our MR experiment. So if you imagine this here is just a classic 2D Fourier transform of an image, what we're doing is essentially sampling one point at a time as we go through here. As we'll talk about in a little bit, you can probably envision that if we want to collect higher resolution images by going farther out in the Fourier transform space, it takes proportionally longer to get out there to collect those samples. Now, once we've collected all these samples, Fourier transform is a fairly simple model of this. It's one we'll use in a number of cases, but there is a lot more effects you can account for here. But what we're faced with now is we have a collection of samples, and we want to create an image out of this. So at heart, this is an inverse problem that we're going to have to solve. There's a number of ways you can go about this. We'll take a very classical statistical signal processing approach to this, and this is what we're going to walk through here. But the main thing to keep in mind is what we're doing is we're essentially constructing an experiment where we're collecting a finite number of samples in some alternative domain, and then we have to go through a mathematical process to transform these samples into an image that we're hoping to generate and then show our clinicians. So, okay, this sounds like a fairly straightforward process. We've talked about the need for speed here, so why is it important to make these exams fast? And I really want to categorize these into 2 different areas about why having speed is important. The first one is that the less time your patient's inside of a scanner, it's going to be very beneficial to the patient for a number of reasons. As you saw in that slide right before, an MR scanner is a big machine with a fairly small hole, and you're going to go in there and it's going to be loud, a little bit cold, and not the most comfortable experience. So if you're able to have the patient in there for less time, they're going to be more favorable to be coming back for future studies later on. From a pure business perspective, we can also look at this to where if we can actually get patients in and out of the scanners quicker, we can increase clinical throughput and ultimately reduce clinical cost of MR scans as well. Another one is that just like a regular camera, when you have a long shutter, shutter exposure, if that's open for a long time, there's a greater risk of motion and the potential for blur in your images. So if you look up here, for example, on the shoulder, where this is a fairly long acquisition, in this case, to where the patient moved just a little bit, you can see that there's some blurring artifact over here, and this can potentially confound the diagnosis, especially if you're looking for small tears right around the cartilage. Whereas over here in the case where there was no motion, it's a lot sharper. Now, another reason that we'd like to look for high temporal resolution is it allows us to really capture and measure physiological processes that we might not be able to describe otherwise. So here's an example where there's been contrast injected into the body and it's flowing up through the arteries and veins. And as we can see, what's happening is it comes up here through the carotid arteries and filling into the vasculature of the brain. It's starting to fill in here, and we can see, and later on we can see as it comes and returns to the venous processes. And when you have this temporal resolution, it allows you to make certain diagnoses that might not be possible if you just had a single image with no temporal delineation here. And we can also use this to look at things like, moving structures like the heart beating, and again, functional information like I talked about before for thought. So, okay, what's the barrier here in terms that's keeping us from imaging fast? Now, most of you in the room are probably familiar with Nyquist sampling, classic concept, and it's really what drives most of the conventional thinking of how MR experiments are designed. Now, we know that, Nyquist and Shannon told us you always need to sample at least twice as fast as the bandwidth of your signal. So that's understood, but from a purely algebraic perspective, if we're looking at this from, solving an inverse problem, if we have some image we're trying to generate which has so many pixels or voxels in it, we really need to collect that many samples to make sure that our system is at least, it has to be well determined. Now, again, as we're looking at this, as we think about this as a serial process, if we want to get these higher resolution images covering an extensive field of view, we're going to need to collect a lot of samples. Now, again, if we think about this as a serial process, collecting those very high resolution images is going to take a long time. Now, here's the trade-off, is we just said that we want to have high temporal resolution. Now, how do we go about trying to get both of these at the same time? There's an inherent trade-off of we can either get very fast images at low resolution or very high resolution images at slow temporal resolution. And we're going to look at how we're going to about trading these off. Now, you might ask, well, modern A to D converters all run really fast sampling. Can't we just turn this thing on and grab all of our samples all at once? Now, plenty of people have thought about going down this direction, but there are some other physical challenges that come essentially with trying to be too greedy and collect all your samples. And essentially what happens is after you apply RF excitation, you do this, your signals start to dephase. And essentially, right after you do that initial excitation, the quality of those signals starts to break down. So you can really only collect them in small bursts. And just to give you an idea of what happens is if you try to be essentially too greedy in this manner, if we look up here around the anterior cerebral arteries, you can see there's a bit of blurring over here. Now what happens is this is actually right above your nasal sinuses, a little air cavity in your head. And there's a small distortion in the main magnetic field there. And the MR scanner, being incredibly sensitive, actually picks up those little changes in the magnetic field around your sinuses there. And if you try to be too greedy, it actually picks up on those changes and essentially overcompensates is a way to think about it. So we have to be careful about how many samples we get at any given time. The point being here is that there's a lot of restrictions, is that we have to try to collect all these samples, but there's also a lot of rules that say how many we can collect at any given time. So, okay, well, what do we do? This sounds like a fairly challenging problem, and you're saying that I need to have all this stuff, but I have all these rules. How do I go about it? So what's the easiest way to go about shortening your scan time? Well, just don't collect all the data. Just only collect some subset of it. So the way I would think about this is, let's imagine all these boxes up here as the Fourier transform of the image that I'm trying to collect. And every element in white here is a sample that I'm actually going to collect. And all of these are roughly collecting about half of the data necessary in these cases. So what it's saying is if I were to only collect the data in the white areas, I would roughly shorten my scan time in half. So, okay, seems like a fairly straightforward way to go about shortening your scan time. But again, the problem is now I'm trying to reconstruct an image where there's more unknowns than samples. I'm underdetermined, and there's technically an infinite number of solutions. So how am I going to go about doing this? And this is what we're going to get into here, is looking at these, what are classically ill-posed problems, and how to actually stabilize these and use other information to where we can actually construct diagnostic quality images from these limited amounts of data. So just a little bit of a lecturing here, just to give you an idea of my common recipe that I use when tackling all image reconstruction problems. This is kind of how I go about it, and something that I recommend anytime I go about talking about this area is these are really the key steps that you want to go through whenever you're faced with a new reconstruction problem. And the first thing, and this is something that most people skip over, is write down what your signal is. The overwhelming majority of MR reconstruction problems that you see, quote unquote, out in the wild don't start at this level. So you just jump into trying to say, how do I solve my problem, but you haven't fully understood what your data actually is to begin with. And quite often, those examples like I showed you with that off-resonance blurring around the sinuses, those are things where if you want to go back later and discriminate, is this a physical effect or something due to the way I'm reconstructing my data, solving that inverse problem, you need to state these up front and really understand what your assumptions are. So once you've done that, you need to identify what your task or goal is. You need to figure out what are your actual unknowns in your problem. And quite often, we have more unknowns than we would like to deal with. So we might need to go through separate calibration processes to learn these up front or figure out other ways of joint estimation or discrimination of these many unknowns that we might face. Now, MRI, as you're probably gathering so far, shares a lot of commonalities with many other areas, both in electrical engineering as well as in the broader inverse problems communities. And when you start to look at things at that level, you realize that there has been a significant overlap in a lot of these problems. And often many of the problems that you'll come about facing have already been solved in other areas. So it's something to consider is that even though it might seem like a fairly niche area, when you get down to the pure equations, most of these problems are not unique to MR. So it's something to keep in mind. And we'll see some examples of this later. Once we've now done this, we can finally go about defining what is our actual mathematical objective. And now we can go start to work this through and trying to solve the problem analytically, something I strongly advocate instead of just throwing a quote-unquote bigger computer at it, because once we do this, now we can finally go and start to tackle use fairly basic hardware to actually tackle very complicated problems. So this is the kind of general recipe we'll be following through here, and I'll try to reiterate on this multiple times throughout the rest of the talk. So here's a basic model of the kind of thing that we might face in an MR experiment. Now, often you'll see in standard textbooks and whatnot, MRI is described as sampling the Fourier transform of your image. I've said this a couple times already. This is a very simplified case of what's going on. It's applicable in some cases, but it's good to be aware of what actually goes on under the hood. And this is not a complete model by any means. So often what we face is, again, there's a subject that goes inside your scanner. Nowadays we use phase arrays very commonly, just like in synthetic aperture radar and other areas like that, to measure our signals. So we have a phased array receiver which will actually collect a set of spatially modulated images. This is just what goes on the reception side. We often have a number of other confounding effects, some of which come from our system. Simple things like the radio frequencies that we do input into the system generate eddy currents with the hardware. We again have other physiologically based non-idealities. It's really good, and I strongly recommend it to state these all up front, and it's better to scratch them off and say you don't need to consider these than to go back after the fact and try to figure out how to incorporate them into your reconstruction models. So just to give you an idea is where we usually typically start with is basically start with the whole kitchen sink model and then work your way down from there. So an example pathway for this might be something called a Cartesian sense-type parallel imaging. This is one of the standard workhorses that's used on almost every scanner every day for all areas of anatomy in the clinic. Now what happens is what you essentially start down and you say, okay, well I have this fairly complicated model over here. And what this says is I have some underlying continuous signal describing the underlying tissue in your body, and it goes through some integral process to come up with a set of data that you measure. Well, okay, this seems like pretty complicated. We can probably make a few assumptions here. Let's say we're doing brain imaging. We can assume that the head is probably not moving. We can make a couple assumptions that if we scan quick enough, we're probably not going to have those dephasing errors I showed you before. And we can assume that a couple of other things like so-called concomitant fields and whatnot are negligible. So we can start to analyze these and say, okay, well, what do we really need to consider? But we know in this case that our sensitivity profiles of our phased array, because we use that piece of hardware, is something we need to keep in our model. So we're going to scratch off a lot of these, but we're going to keep one extra one over here. So now we've gone through and we've simplified our model. Well, a practical thing, and often what you'll see in a lot of textbooks, is people will use integral-based models for solving your inverse problems. Those of you familiar with tomography are probably familiar with the Ram-Lack filter, which is one way of doing filtered back projection. And it's one of those things which is very nice on paper, but it has absolutely no use in actual practice, because unless you have continuous data, no integral models will ever have any real use in a real-world scenario. So it's something where you actually need to account for discretization right from the very beginning if you want your models to be correct from end to end. So now that we've gone through this discretization process, things are starting to look a little bit simpler. This is starting to look like a fairly standard inner product over here. And if we abstract this, it becomes a fairly simple matrix equation in the end. So what we've done is we've walked through, again, a series of steps or a basic recipe to go from a fairly complicated physics model to something which looks quite manageable. So okay, well, if we're able to reduce these things down to a fairly simple model like this, what's the problem? Why am I here talking to you right now? Now, a lot of the clinical workforces and the techniques that are used in routine clinical practice, the ones provided by the vendors, they're meant for, again, very, common. They're kind of meant to be a jack-of-all-trades application is the way to think about them. And the reason that they're so common is that they're very fast. They're not typically non-iterative methods. You can really, paralyze the heck out of them and everything. Computationally, they're very cheap, again. You can really leverage trying to optimize them in your hardware. But one of the real main reasons is that they're also simple, both from a mathematical stance and from a computer implementation sense. So it's something to which there's not a lot of later management. So it's overall a fairly simple concept that the vendors have tried to say, let's get something out which works, and it works efficiently, but it might not necessarily be the best, or squeeze the most information out of our data. Now, one other reason that this kind of a pathway has persisted is over the years there's been a lot of devotion of research effort to optimizing hardware on the system. The whole notion of how do you generate images from the data you've collected has often been an afterthought. It's been, okay, we'll worry about getting the best data out from the scanner, but then once we've got that data, let's just do something fairly simple afterwards. Well, just like with Moore's Law, we're really reaching the limits of what hardware can do, and we're really having to switch over to more software-based solutions and really trying to optimize what information can we get out of this data? How do we make the most of our data overall? Now, what happens, and one of the trade-offs of going down this road of these faster, cheaper methods are that these numerical methods often are unstable. You often get things like noise amplification over here to where you become very sensitive from ill-conditioned systems. These techniques can have blurring in them, and just a number of, you can think about it as a type of aliasing. And it's the kind of thing is, again, you're making trade-offs here where you're saying, let me take the mathematically simple approach, but there's going to be consequences for doing that. And what we're going to try to do is come up with alternative pathways that don't have these same consequences. So kind of the two main areas that we're going to look at in terms of essentially making the most of our data here are, again, suppressing noise and improving numerical stability, but also mitigating kind of these aliasing or other artifacts that can come from taking shortcuts in a sense. So two examples here where I'm going to describe on the top are linear reconstructions. These are kind of classic linear estimators. These are the kind of things that you, again, would see routinely in the clinic. Versus what we're going to call sparse reconstruction, which we haven't gotten into yet, but we're going to be talking about. Hopefully you can see in this case here, the signal-to-noise ratio of this image is significantly increased relative to this one up here. These are two cross-sections of the calves. Now again, this is the exact same scan and the exact same data, and it's really just two different estimation techniques of trying to, again, maximize the information we extract from that same set of data. Same thing over here, exact same scan, exact same set of data, whereas if we use the technique that comes off the scanner, there's going to be a lot of, again, aliasing artifacts over here, these residual lines, which could be confounded for some type of pathology. And again, by doing more advanced processing, which leverages a priori knowledge that we have about both the system and the anatomy that we're targeting, we're able to get a much cleaner picture without those artifacts in it. So what do I mean by a priori knowledge? Now, this sounds like a fairly abstract concept, and it's meant to be, but it's something to which we do it every single day in a lot of applications, and we really just need to think about, how do we go about, again, most of our daily interactions, and how can we transform some of these concepts over into here? So let's look at this example, a Wheel of Fortune here. Let's say we're looking at this board, and we see that there's 5 letters missing, and we need to fill these in. So if we raise, 26 to the power of 5, we get about 12 million possible combinations here. Are we going to go and sweep through all of these? No. The first thing we do is we know that this is an English language show, and then we go down here and say, okay, well, there's going to be certain rules about grammar and syntax with the English language, as well as we're given context that this particular puzzle here has to do with showbiz. And once we start realizing that, we don't sweep through all 12 million combinations. We quickly come up with a set of solutions, and we're able to narrow this down and figure this out very, very quickly. And again, this is the idea. We weren't given, this is a specific set of letters here. We were given some fairly abstract concepts, and this was essentially allowed us to narrow down our search space and come up with an answer very quickly. Now, again, we do this in lots and lots and lots of different applications out in the real world, but the question is, how do we translate this over into something we can use in image reconstruction? This really gets back to Occam's razor, in a sense, and what it says is it's a folly to do with many what can be done with few. Now, when we go back and we think of, this is the original question we posed, was we're only collecting a finite amount of data in one of these accelerated scans now, but we want to reconstruct maybe a very high spatial or temporal resolution image. And again, there was this imbalance of I only have a few samples, but lots of unknowns. Now, okay, what it says, though, is maybe that there's some information or a priori knowledge hidden in that data that I can exploit, which says this is actually sufficient for reconstructing it out of there. It's not going to work in your classic Nyquist sense, and Nyquist-Shannon being about as pessimistic of a sampling theorem as you could possibly hope for. But if we start to look into more nonlinear sampling theorems, it actually says, hey, we might actually be sufficient from an information theory perspective. So again, going back to Occam in that case, really what was going on was we were saying we're targeting something which is simple. And again, that's kind of the same thing that was going on in that wheel of fortune example there before, is that we're targeting what was essentially the simplest solution out of all those possible letter combinations. Now, well, what does it mean to be simple in an imaging context? Well, let's look at this phantom image over here. Now, when we look at this phantom image, you might look at that and be like, yeah, there's not a whole lot going on in this image here. This is just a cross-section of a physical phantom made out of plastics. Now, we look at this and we say, well, again, what does it mean to be simple? The first thing, especially if you come from an image processing background, you might say is that the image is fairly piecewise constant. It's fairly homogeneous in a number of regions, like over here in the center and these circles over here. They're fairly flat. So that's already heading down this road one way, but we can take that a step further and say if we were to take the spatial gradient, essentially the spatial derivatives of this image, we can see that it highlights that the information is actually only on the edges here. Now, for those of you familiar with image compression, this is the basis of all image compression, is transforming your image into a domain that makes it a lot simpler. Just like JPEG, you do local blockwise discrete cosine transforms to make that image a lot simpler and reveal where the information actually lies. Now, we can quantify this by using something what's called a zero norm. This is basically a fancy way of saying, let me go count the number of elements in my image, which are either 0 or non-zero. And what this provides is a quantitative metric of how much information is in my image. And if we go and further say that the total number of essentially information components of that signal are a lot fewer than the total number of elements in that zero, we're going to call this sparse. So in other words, we're going to say the information is sparse in this transformed image. So, okay, that's great. But what happens if I'm now faced with a situation to where this is the thing that I know I'm chasing after, but all I'm again given is a set of points in this Fourier transform space over here, and again, particularly this undersampled space. So how do I go about actually trying to solve one of these, use this information? What we can do is we can set this up in a more Bayesian regularization type sense, to where I can say if I've given a standard linear system model over here to where I have my image F that passes through an undersampled Fourier operator A, and then that gives rise to the data that I measure. So it's essentially a linear system model to where A is an underdetermined operator. Well, if I know and for MR, noise is just zero mean Gaussian, so I can set up a least squares estimator. It's going to be your maximum likelihood estimator. And I can set up a standard least squares regression over on this side and say, well, let me find the image which matches my data in a least squares or maximum likelihood sense. Well, additionally, I can go over on this side and say, well, okay, but we've already said it's underdetermined. There's probably going to be an infinite number of solutions in that case. That's probably not enough. So what I need is I need to incorporate this notion of sparsity here. So I just gave you a second ago this L0 norm. It's a metric which counts how much information is in here. So what we can do is we can put this as a penalty, which says if I take my image and potentially transform it in some way, if that image is sparse, that value should go down as well. So now what we're given is a balance where I've got this cost function which consists of something which says my image must match my data, but it also must be sparse at the same time. And I'm given the option of how do I go about trading off between these two quantities. I want to promote my data to match, my image to match my data, and I want to promote my image to be sparse at the exact same time. So, okay, that sounds like a fairly straightforward concept, but why should this kind of thing actually work? That's probably the question at hand here. So the first thing to look at is kind of a reduced case of this and kind of show why does setting up a regression problem here actually induce sparsity in our solution. Now to start, what we're going to do is we're going to have a synthetic 1D signal over here. The blue signal is the real one. The red one's going to be my noisy measured one over here. And what we're going to see is that the blue, you can see there's actually only a few non-zero components in that true solution. But again, that's not what I'm given. I'm given the red one, which is not sparse. Now we're going to look at three different signals here. We're going to look at the reduced case to where we have no transform. We're essentially an identity transform operator. And the reason we're going to do this is because for each of these different signals, we can actually get a nice closed form solution for what that optimal value is. And additionally, for these experiments here, just assume that the regularization parameter, the optimal mean square error value, is given by some oracle. So we're just going to assume that for the moment. So if we look at this, we look at the zero norm case I just talked about. If we look at the transfer function from input to output over here, what we see is that the optimal solution corresponds to a hard thresholding. Essentially, for some threshold range over here, which is determined by that regularization parameter, anything below that value in magnitude is going to be set to 0, whereas anything above that value is going to be preserved. For those of you in statistics, this is known as subset regression. This has been very commonly used in a lot of communications applications. But if we look over here, what we see is going through this estimation process, you can see that we do generate a sparse solution. So in other words, this seems like a very good direction to go because we are inducing sparsity in our result. The problem is that when we generalize this from the case of going from an identity transform to a non-identity transform, this problem becomes NP hard, and we can no longer solve it in any practical sense for anything other than a trivially small signal. So, okay, great concept, but again, we're back in the situation where this seems to have no practical utility. So let's go to another case. Let's go and say we're going to do just this classic L2 regularization statistics known as ridge regression, also known as Tikhonov regularization, Wiener filtering. All of these wind up being essentially the same concept here. And what we see in the I/O transfers is essentially just rotated our input-output function. And the key takeaway thing here is that unless you started at 0, you don't become 0 afterwards. In other words, we are not inducing sparsity. And if we think about it as to where we're actually measuring a noisy or stochastic signal, the probability of actually being 0 to begin with is 0 itself. So in other words, you are never going to actually create a sparse signal from this type of a process. And if we look at this over here, we can see that, yes, we actually didn't induce sparsity in our result either. So again, classic tool, widely used in a number of applications, but doesn't seem to be helping us here. So okay, I had one more signal method up here, and this was the so-called L1 norm. So instead of taking the sum of squares or the sum of just counts, let's just take a sum of absolute values, the kind of intermediary point between these two. And now we look at this, the kind of I/O transfer function here is something called soft thresholding, where within some thresholding range, we are setting them to 0, but anything outside of the range isn't exactly being preserved. It's being shrunk down a little bit. This is known as soft thresholding, lasso regression. Again, another couple of techniques you might have heard of. And the key thing here is that what we see is we are actually inducing sparsity here. So what we're seeing, it might not be doing it quite as well as a full L0 norm case, but it is actually achieving our goal. Now, the key thing about this is that L1 norm is a convex function. And since this was just adding on to a least squares regression, which was also a convex function, this is a convex optimization problem, which means it has a single global optima which can be achieved by any of a number of standard numerical optimization techniques. So in other words, we've gone from something which was essentially NP-hardened combinatorial to something which is now tractable. Now, the real interesting thing that came out of this was people were aware that you could have these sparsity-inducing methods for a long time, but it was only about 10 years ago when the group at Stanford, led by Dave Donahoe and Emmanuel Candes, figured out why this actually worked. And essentially this came down to a technique which is now known as compressed sensing. And what this says, if we think about in the analog of Nyquist sampling, where you sample at twice your bandwidth, what they were able to prove was that in your transform domain, your signal had at most k information components, k non-zero components. You only needed to sample at a rate of about 3 to 5 times k to guarantee that signal was recoverable. So in other words, rather than sampling at a rate proportional to your bandwidth, you sample at a rate proportional to the information content of your signal. And there's lots of generalizations of this where you can account for different noise effects, the interaction between your sampling and transform domain, et cetera, et cetera. But the key takeaway message here is that this isn't just a technique which was, nice and seems like it works. There's a very provable reason as to why you can get away with sampling in this case, with as few samples in this case. And the key thing is that you need to know something about where your data lies. You need to know how to transform it into an efficient representation. And then you also need to solve a certain type of nonlinear optimization problem to guarantee that recovery. And it's really that package of those two things is what enables you to go from a fully sampled image like this, having a very restricted set of samples, only about 20% here, whereas something like a Wiener reconstruction would give you this blurred result versus the L1 norm or compressed sensing reconstruction you can see gives you essentially an exact recovery from only about 20% of your data in this case. So, okay, this seems great. This seems like this has a lot of potential. And when this first came out, I remember I was sitting in a conference when I first saw this and basically, threw away everything I had just spent the previous 5 to 10 years learning at that point because everything was, classic Nyquist sampling, linear theorems, et cetera, and all of a sudden it was saying, hey, you don't need to do any of this. And like many people at that time when we saw this, were like, this is a lot of it, and everybody went out and said, this is going to work great in my area. And for me, this happened to be medical imaging here. So I obviously wasn't the only one looking at this too. And all of us that really started looking at this were like, okay, well, how do we use this for MRI in particular? Because there's this real need to get away with having fewer data and really speeding up our scans. Well, some practical challenges, number one, is that a lot of MR images actually aren't that sparse when you look at them. And this is something that a lot of people, especially from the image compression field, really missed on, and where a lot of this work had been done. Now, when most of those who work in image compression, you're worried about making an image which looks pretty close at a high level to the thing that you started with. You don't really care about the details too much. It's really that kind of bigger coarse picture. Well, in MRI, it's the absolute opposite. If we look at an image like here, and we just look at these little tiny features right here, turns out those are lesions caused by multiple sclerosis. Now, if you're using something like a total variation function, which induces piecewise homogeneity in your image, you could have a simple little compression artifact which mimics an MS lesion. That's not a good thing. So you need to be very careful and take on a slightly different mindset about what you determine as image quality and recoverability when you start to go with these things. One of the other challenges is when these first started, a simple little Shep-Logan phantom, the phantom in MATLAB that you can generate, it's about a 128 by 256, 128 by 128 or 256 by 256 pixels, little tiny image. It took about 4 to 5 hours to do a single reconstruction using some pretty advanced optimization tools at that time. So there's this clear trade-off between how much time you spend acquiring your data and how much time you spend reconstructing your data. Well, clinically, we often do 3D, 4D, 5D, et cetera, data, as well as these need to be turned around very quickly. So there's this issue of scalability. Radiologists can't be waiting days or potentially a week to get a single result back. These have to be coming back very quickly. So there's a huge computational gap when all of this started. And again, details matter. And there's also this question about, how do we start doing things like quantifying performance? If we look at things like SNR, mean square error, all the classic sense, those start, they're not quite as simple anymore when you deal with nonlinear estimators. And you have to look at some different ways of quantifying how you actually measure performance in these cases. So this really raised a lot of questions of great idea about how do we actually go about using this. So this really raises the question of like, okay, well, it seems like the odds are really against us here. Can we actually make this work? And the answer is yes. So these are, I'm just going to throw up a couple of slides here. These are initially from a tutorial given at the IEEE ICIP meeting a few years ago on this. So here's some work, and one of the original pioneers of this was Michael Lustig at Stanford, who was one of the doctoral students under Dave Donahoe, who invented a lot of the compressed sensing theory. And they were really the first ones to recognize that translational concept about how this compressed sensing theory could benefit magnetic resonance imaging. And as you can see in this case here, this is something called auto-calibrated parallel imaging. For those of you in the audience familiar, this is the standard Arc Reconstruction on GE scanners. This is a cross-section of the body in a pediatric patient. And we can see the kind of descending aorta here going down and branching down into your legs. These are your intestines and such. And you can see for this highly accelerated scan, where they're trying to really image this kid quick because they don't want to have to put him under anesthesia, there's lots of noise, and especially over here up in these kind of vessel areas, you can see that a lot of the anatomy is just buried under the noise. So it's okay, we got the image really quickly, but it's not really diagnostically useful. Well, but instead, going through one of these nonlinear optimization problems, you can see, again, exact same data. All of a sudden, all that anatomy is popping out. It's not being buried under the noise. And all of a sudden, you're having something which is both fast and clinically useful. Now, to start with, these images weren't particularly, took them a very long time to reconstruct, on the order of many hours. But as I'll show you in a little bit, they've since gotten this down to running multiple of these a days at Lucille Packard Hospital out at Stanford. Similarly, here's some of our own work at Mayo Clinic, to where we were looking at the case of time-resolved angiography, to where we were going and injecting contrast into the body and using that to create very high spatial and temporal resolution images of blood flow and essentially how that contrast goes to the vessel. So this is a case of a 2-year-old who suffered a stroke, and this is a cross-section going through the side of the head, essentially a sagittal view here. And sense here is the standard clinical result, and this is, again, this is a very highly accelerated scan. And what we can see is you look at this, and it seems like usually areas of enhancement are areas where there's been some type of damage or pathology in this case. And you look at it and you say, oh, okay, it looks like there's something going on here that could be suspicious, but there's also some other stuff all over here. So the radiologist brought this up, and we're like, we're looking at this, and we think there's something there, but we just can't see it at this time. So I get a phone call, and it was, okay, can we run one of these iterative reconstructions? This is when we were first getting started on this. And this is, again, the result here that we got out of that exact same data. And hopefully you can see over here, the difference is this isn't buried under noise or anything now. This pathology is popping up, and really what this is the area of ischemia in the brain post-stroke, and it was showing contrast absorption. You can even see the folds of the brain popping out over here. And what this was showing was that the area of tissue, because the child was so young, it was actually starting to recover a little bit. And they were able to make a much more confident diagnosis in this case here. So again, same data, running the reconstructions actually changed the course of diagnosis in this case. We've since applied this to a lot of other different anatomy. You can see, again, a contrast enhance of a diseased foot here. You can hopefully see in this enlargement here just lots of small vessels popping out. You're able to look at much, much finer anatomy that you wouldn't be able to see under a standard clinical scan here. It really pops out by solving one of these nonlinear reconstructions. And we have applied this to a lot of different cases. And as I mentioned earlier, by really driving back to that kind of core physics and making sure you account for everything from the very beginning, that blurring from that off resonance around the sinuses I showed you before, we can, rather than trying to figure out, well, how do I handle this after the fact, we just put it in our model, propagate it through, and it's taken care of. So hopefully you can see over here what we get is that not only do we get the sharpening that we get by taking care of that physical non-ideality, we also, again, get those S&R improvements from the iterative reconstruction by using these compressed sensing techniques. So in other words, we're really able to put everything together in a very synergistic manner, which is mathematically correct and allows us to really leverage advanced optimization tools. Now, because we've gone and we've developed, again, a very succinct model which accounts for things from end to end, we can further take this and actually start to develop in-house high-performance numerical optimization techniques. So this isn't just using MATLAB's FSolve. We can actually go and develop our own tools that go from scratch, and we can really look at saying, well, if we look over, example, minimizing a cost function over the course of iteration, how do we drive that down and make that converge as fast as possible so we can terminate it quick and get those results back as fast as we possibly can? So again, we've taken this also to developing a large number of in-house numerical methods to where we now solve these very large-scale problems in very efficient manners. As I mentioned, I'm not the only one doing this. We saw the example from Stanford. Here's one from Mohammed Usman and colleague at King's College London, where they've gone and incorporated various motion models for cardiac imaging. And as you can see over here, what they're able to do is significantly sharpen up. You can see improved depictions around the myocardial walls over here. What they do is they take advantage of the fact that the heart is beating in a very periodic manner. And if we look at it as time series, we take a Fourier transform through time, that periodicity really pops out, and that's what winds up being our sparsity. So we're able to take advantage of that through time redundancy and the periodicity of cardiac motion in these cases. We can do other ones where we can start to look at multiple chemical species. I told you that we can tune the MR scanner to different species. Well, sometimes we can essentially, in certain ways, tune it to two at once, where we can separate fat and water, which actually have two different chemical resonances. And in doing so, we can come up with things like what is the fat fraction of a particular tissue, or remove the confounding visualization of fat in your images. So you can see over here where we can separate areas of water and whatnot versus fat over here kind of around in the neck area and up around the scalp. And we're just able to separate these. There's lots of games you can play, and again, by going end to end, you can come up with almost any scenario you like. We can do this in things like diffusion, where we can look at higher dimensional spaces and not subsample in an image, but we can subsample in other spaces as well. This is work by Luca Marinelli at GE Global Research. And the point being here is this is an incredibly flexible framework. And by starting from the ground and working all the way up, you can really apply it to almost anything you want. So, kind of going beyond these straightforward applications of sparsity, where are things lying at now? I mentioned one of the big challenges is that, I was going to say, whoever's got that, if they could turn it off, it'd be appreciated. Thank you. One of the things we've been looking at is how do we quantify performance here? Now, again, things like classic S&R aren't really what a radiologist judges image quality based on. Now, when this realization really came forward, we were like, okay, well, at Mayo, we have a whole set of quality control tools that are used to evaluate every MR scanner every day here in our fleet of about 30 scanners. And if these are used to evaluate the quality of a imaging performance on a scanner, can we take this further and actually hijack these and use these to prove which of our techniques are doing better in certain situations? So we hijack some of those quality control tools, and through this, we're able to actually show one of the kind of lingering concerns out in the general MRI community when all these techniques came about was that if we're performing all these various thresholding methods and so on, we're probably going to be thresholding out low contrast signals, which are often the things of greatest clinical concern. And what we were able to show is that through these here is that if we actually have a formal measure of low contrast detectability in these QC scanners, as we decrease our sampling rate, turns out despite the fact that we're doing this, we actually hold on to low contrast signals better than the conventional techniques that don't use these thresholding. So we're able to actually go and kind of dismiss a lot of these concerns along the way and chisel them away and really get greater acceptance by a lot of the clinicians. But really, at the end of the day, and what the Stanford group has really pioneered is doing formal radiological evaluations. This is something we do now too. But at the end of the day, it doesn't matter what all your fancy numbers say. It's whether the radiologist says there's an improvement or not. So this has really been the driving factor in what determines good image quality from all of these methods. And I'll skip over that. So one thing I talked about before is I mentioned that a single image often took on the order, a single Shepp-Logan phantom image took on the order of, many hours to days, et cetera, to reconstruct. So how do we actually go about trying to make these things practical? Now, around this time, this is probably around 2009, 2010, when these things started becoming a big concern, Stanford started teaming up with GE and looking at various GPU-based computing solutions and really trying to push the performance of their algorithms in these cases. Now, in doing so with a multi-GPU system, they were able to get those pediatric results I showed you earlier down to about 1 to 3 minutes for a 3D reconstruction, so significant improvements. And they were able to get this up to about 6 cases a day at Lucile Packard Hospital. Around the same time, we here at Mayo partnered with Intel. For those of you who have seen the kind of many integrated core architectures, now known as the Xeon Phi, we worked with them to also at the same time adapt our algorithms to work and be optimized on that hardware platform. And in doing so, we're able to get one of those 3D contrast-enhanced angiography examples I showed you down to about 12 seconds per volume. So orders of magnitude improvements, clear scalability in this case, and it was really the first essentially inline demonstration that this technology could go from this very nice topic down to something which could be made clinically practical. And again, it was also a very nice partnership where we were able to kind of combine the expertise of Mayo's both clinical side, numerical optimization side, and Intel's high-performance computing to really come together and take this essentially to the next level. Today, these are down to about 1 to 2 seconds in this cases with some other computing solutions. So where we're at now is kind of in a combination of high-performance computing and, again, some of these very custom numerical optimization tools that we've developed in-house. We can now take a full time resolve. This is a 4D exam, 3-dimensional volume changing through time, in this case for prostate cancer imaging. And what we're able to do is have the data come off the scanner, go to a dedicated online computing server, and be back at the radiologist's workstation in about 3 to 5 minutes for the whole thing. So in other words, again, keep in mind a single simple 2D image from the past where it took many hours, we're now able to do 4D data in just a matter of minutes. And in doing so, we've now done over 3,000 patient exams since summer of 2015. We do over a dozen of these each day here. And it really shows that by really chiseling away at both the mathematics and computation, we can drive this from just a nice concept down to something which really changes clinical practice. So to kind of wrap up here on the very end is I've talked mostly about cases of classic compressed sensing to where we'd look at vector-type signals where we take an image, we treat it as a single vectorial quantity, and we apply a linear operator to it to put it into the domain that reveals information. But really, we have a lot more information going on in a lot of the data we look at nowadays. For example, if we look at a time-resolved image of the heart beating, we can see that, yes, the heart will beat in and out over time. We have space in a 2-dimensional signal here, but we also have multiple channels of a phased array. So our data here is intrinsically 4-dimensional as it is. So how do we start applying some of these concepts of simplicity in these higher dimensional spaces? Now what we can do is we can say, let's actually look at our data as a matrix quantity to start. So one thing, and just a quick recap on linear algebra to kind of preface some of this, we're going to look at a matrix here, and we're going to say, a matrix is really just a 2-dimensional quantity. And for those of you who have looked at eigenvalue decompositions and whatnot in the past, they're essentially information-revealing methods for matrices. Singular value decomposition is a way to do this information-revealing process for non-square matrices, lots of stuff that we deal with in practice. Now, when we look at this, what this does is it really just, it's a standard decomposition process that reduces the matrix into the product of 3 different signals. And if we look at the kind of the singular value matrix, the one that contains all of our information in there, well, the rank of a matrix, really what tells us how many linearly independent rows or columns in our matrix, is really just a count of how many singular values are non-zero. And if we think back to the very beginning of all of this, the way we defined sparsity was just the count of non-zero elements in our image. So it turns out things like eigenvalue decompositions and singular value decompositions work in the exact same manner as all of this sparsity stuff. This is how we bridge going from the linear transformations to these higher dimensional spaces. It's actually by going back to fairly classic linear algebraic concepts. So what we can do is we can look at something like the beating heart. This is my heart for reference here. You can see it's going back and forth. And if we look at this image going through time, what we can see is it kind of breaks down into kind of two areas. We have areas which are fairly static and areas which are moving in a fairly regular manner, such as over here. Now, let's say we were to take this image and we were to rasterize each image out, and we're to stack up one column where every column of our so-called Casorati matrix here represents one of these images in time. So in other words, each column represents one time frame. Turns out that if we go and compute the rank of this matrix, because so much of this space is not moving, and those parts that are moving in a fairly predictable manner, this matrix will be very low rank, or there'll be very little information. The eigenspace of this will be fairly compact. Now, just like we looked at things before, we can set this up as a regularized estimation process, but instead of having our sparsity measure over here, we just swap in what is essentially the higher dimensional generalization of an L0 or L1 norm. We swap in either the rank measure or something called a nuclear norm, which is really just the sum of the absolute value, the sum of your singular values. So in other words, all of the convex optimization concepts scale up very naturally using basic linear algebra concepts. Now, one of the challenges that we face in MRI, though, is that often, unlike things in video compression where you have many low-resolution images, we often have just a few high-resolution images. So if we look at this Casorati matrix of space versus time, it's very, very asymmetric. And what that means is that we actually have very limited degrees of freedom to play around in. And if we try to use these rank concepts right away, it turns out that we actually don't have much space to play in. What our group developed was a way to actually go and break this down, kind of like you do, again, in a JPEG-type fashion, into a series of overlapping blocks, to where we have a large set of overlapping spatiotemporal blocks, and we actually analyze the rank of these all in parallel simultaneously. And as we can see over here in this time series, if we were to look at the rank of one of those spatiotemporal blocks, we can see it drops off very quickly. In other words, when we look at these, there's actually, very little information actually contained in each of these, and this is something that we can go and exploit. And it turns out by going this way, this is a joint work with Stanford, we were able to actually formally prove that going to this local low-rank framework over the global sense actually gave us lower mean square error than was possible by looking at things kind of overall. And we can see over here just an example from kind of essentially picking the minimum mean square error optimal parameters. If we look over here by the tricuspid valve, you can see whereas this noisy image over here, yes, it's present, but there's noise around here. When we do the global mean square optimal thresholding, you can see there's blurring through time. That tricuspid valve area gets blurred out. So even though we're removing noise, there's an expense for this. And at the other end, if we use the local concept, we get the best of both worlds. We get the complete noise reduction, and we get preservation of the anatomy. We can take this a step further for looking at things like our phased arrays that we talked about earlier. Now, I mentioned before that, we needed, essentially was the spatial sensitivity of our phased arrays. We kind of brushed over that before and said, okay, we're just going to kind of assume that's a known thing through some calibration process. But what happens if we actually just, step up and say, hey, I actually don't know this. I need to take care of what is that calibration system as well. Well, that means my system really has at heart two unknowns, the physical responses of my receiver hardware and the image that underlies it. So if we do this, one of the challenges is that you say, like, okay, well, when I do a separate calibration scan, what happens if the patient happens to move between when I do my calibration scan and when I do my actual scan that I care about? Well, if the patient moves in that case, you can start to get artifacts that go in between here. So you get this basically misregistration inconsistency. So it'd be really nice if we can go and actually not have to deal with this and essentially say, is there a way we can handle all of this implicitly rather than explicitly? Now, again, a different group at Stanford also worked on this, and they first started tackling using low-rank Henkel matrix regression techniques, stuff very similar to what's used to do recommender systems, for example, in Netflix and whatnot. When the Netflix prize came out a couple years ago, this was a lot of the math that came out of that result. They were able to actually lay out the foundational concept that, yes, you can actually extract both of these signals in parallel and essentially combine them down at once and come up with what's known as calibration-less parallel imaging. So in other words, in a case where we just have a whole bunch of random samples, if we were to do a classic Wiener-type reconstruction, yeah, pretty much buried under all the aliasing, whereas if you do this concept, you pull that right out. We don't have to jointly estimate anything anymore. The problem is, this is all based on singular value decompositions of very large matrices, and SVDs have cubic complexity, so they don't scale very well. And it turns out these things take a really, really, really long time to compute. So what we did is said, okay, well, if they're looking at things globally in the Fourier transform domain, the dual of that is look at things locally in image space. And if we do that, turns out that there's actually some physical reasons about why these matrices should actually be low rank as well. And it turns out by Biot-Savart laws for the RF hardware, because the spatial response of our coils should be smooth, we can leverage that. And actually it turns out that the spatial responses being spatially smooth means these little matrices are going to be low rank. So just like I showed you where that auxiliary dimension was time for cardiac imaging, if we do that same local concept here to where our auxiliary dimension is the receiver hardware index, turns out that's low rank too, and we can use the exact same optimization framework and come up with an image domain calibration-less parallel imaging method as well. Lots of advantage for doing this. You can do a formal complexity analysis and show that we get over 2 orders of magnitude improvement over the full global ensemble K-space approach. And we get essentially the same results here as them, whereas again, Wiener-type reconstruction, lots of aliasing. In these cases, we get perfect reconstruction from essentially 1/3 of our data here, except whereas on a serial MATLAB implementation, their method takes about 3,000 seconds, we're at about 42. So you can see in practice, we are getting that 2 orders of magnitude improvement that the theory predicts as well. This scales to a lot of cases. We can apply this again, lots of different sampling patterns, different types of MR acquisitions. Those examples I showed you earlier with the artifacts, you can see that these make them go right away without having to do separate calibration processes. And we can, again, apply these to lots and lots of different scenarios. Here's spiral imaging, accounting for some of those off-resonance effects. And we can even do things like incorporate accounting for the fact that our gradient systems in our MR hardware might actually be linear, like all the theory predicts, so there might be some nonlinearities in here. And we can start to incorporate those and start to actually squeeze just a little bit of extra resolution out, which turns out has been hanging out in there for about 35 years, and it's something which we were able to pull right out after the fact. So again, by going back to the heart and really working these things out, things which you might not even think about giving a second look, it turns out that there's often a lot more information that's hidden underneath all of these. And again, one of the nice things is, again, by building these up from a very foundational level, we're able to combine things like compressed sensing and these high-dimensional concepts. We can get them to play synergistically, and we can do things like push them further by going to a 3x acceleration. When you have 3 times less data, you do take a little bit of an S&R hit in general, but we can then recover that by using these sparsity concepts. There's lots and lots of different games that you can play. And I'll skip a couple of these. So to finally end this is to go like, let's take this really all the way and now throw in the complex scenario to where we have all of these different dimensions, that 4-dimensional signal that I just talked about a couple minutes ago. Well, really what we have is basically a 3-way tensor structure here where we have space, time, and phase array receiver channels. So how do we scale up all these compressed sensing concepts to this very high-dimensional space? And I was really just looking at it in the same way of, okay, well, all we need to do is translate this into a mathematical concept which we understand and have existing tools for. Well, one thing we can do with tensor structures is we can always unfold them. And if we have a 3-way tensor, there's going to be 3 different unfoldings where each of your different dimensions will represent one of your independent dimensions of your tensors. So for example, if we have space, times, and coils, we can unfold these in different ways to where we concatenate coils and time and have space as an independent dimension, concatenate space and time and have coils, and concatenate space and coils and have time. There's 3 different ways of doing this. Now, hopefully you can start to look at this to where if we were to say, okay, well, we've got space versus coils, space versus time, these should sound pretty familiar. These are the techniques that we just talked about. So those are all just special cases of this more general framework. And it turns out that if you actually work out the details on these, it turns out you can actually explain why all of these signals should exhibit these low-rank properties in these high-dimensional spaces. It's not just a matter of, hey, I tried it and it works. We can actually, again, dig down into the physics and explain this is why these high-dimensional signals should be low-rank in these reduced tensor spaces. And just like we did before, we can set this up. It's a little bit, getting a little bit more complicated here, but we can set this up as just one other nonlinear regression, and we can walk through, again, all of our same numerical optimization processes to work on solving these things. We can start to use some of those other tools we developed, like those unbiased risk estimators, to look at how do we optimally choose the different parameters and try to figure out, ask questions, do we need all of these different unfoldings, or does one of these particular tensor unfoldings provide us the dominant amount of information and let us only focus on that one? So we've done some work looking in that realm. And we can develop, again, customized numerical optimization procedures to where we go and actually incorporate all these multiple tensor unfoldings. We can do things like incorporating sparsity through time for cardiac imaging, like I talked about. We can put all these together and then develop some custom optimization techniques to actually solve these in a very efficient manner as well. And just to show an example, here's I think this one's a 4X cinecardiac scan over here. So again, this is what would be your normal fully sampled scan if you had collected all of your data. And what we're going to do is pretend like we only collected about 25% of that. And if we were to use a standard so-called sliding window, a linear type of reconstruction for solving that, you can see that there's some aliasing up here in the sampling dimension. There's all these other artifacts here. Whereas by using our advanced reconstructions, not only are we recovering all the anatomy, you can actually argue that the SNR is better than had I had all the data in this case under a naive reconstruction approach. So it's really what it's saying is just having a subset of your data isn't the limiting factor. What it really comes down to is how well do you make use of that data that you have. That's really the takeaway message here. As you can see over here again, improved preservation of the anatomy. If you look at the anterior septum line, sharpened over here despite the fact that we're missing data. Tricuspid valve area over here, again, preserved high SNR. And again, really what it comes down to is really working end-to-end and really trying to make the most of what you know and then really working through and make sure that you use that knowledge that you have in the best manner possible. And just a couple more examples. And again, hopefully you can appreciate the advantages of heading down some of these nonlinear optimization roads and what it can potentially buy you, especially in clinical practice, and looking at the clinical potential here. So, in summary, I've talked about the need for speed in MRI and kind of described a general strategy that I take in particular for MRI reconstruction. Overviewed the application of sparsity and compressed sensing type concepts to a bunch of different MRI applications. And then we've looked at various open problems that exist in this area, as well as what are essentially, where is the field going? How do we take this to higher, a lot of the quote-unquote big data type applications that we face in imaging where we have lots of different dimensions? And how do we really tailor these techniques to exploit them? But at the same time, keeping in mind that we want to look from end to end, make sure that everything is theoretically sound and really squeeze as much out of our data as possible. Where a lot of this is going nowadays, even though we're one of the few sites to actually have a lot of this technology translated clinically, this is something to where there's still a significant need. Only just in the past couple of months have some of the vendors announced that some of these concepts for our basic 2D and 3D applications will be available commercially. So there's still a big gap between academia and industry in that sense. And a lot of this really comes down to making these techniques be able to be used seamlessly within a routine clinical workflow. There's also a lot of interest in generalizing these things to so-called quantitative imaging, to where we not just have linear system models, but we now have nonlinear system models. And instead of chasing after an image, we chase after some underlying physical parameter that might have undergone through some nonlinear process. So the way to think about this is whenever you fit a line to your data, what you're doing is you're really going after the slope and intercept in that case, is the parameters. Now, what we might have is some other nonlinear models describing our data. Can we chase right after those parameters directly? And there might be some advantage of doing that in this type of a framework. And as a lot of this stuff comes out, especially on the optimization perspective, there's still a lot of things that aren't necessarily well understood about performance of these type of approaches. So there's still a lot of coarse signal processing theory that needs to be matured. So these slides overall, a lot of people to thank there, so you can read the list. But any questions overall about any of this? So I would say there's two realms for that. If you use general black box solvers available from existing packages, then yes, widely, because you fall into the jack of all trades, master of none realm. If you actually develop your own, so everything shown here was completely in-house numerical solvers written from scratch. All the problems have been translated. All we're facing are convex optimization problems, which have no local minima, and if you set up what I would call a proper optimization, there will be no stability issues as guaranteed convergence, and no matter what, no matter where you start from. So it's a matter, and you can set them up in such a way that really how close you are to your solution comes down to a tolerance which you decide at which point you want to call convergence. But really, it's not a matter of falling into a local minima, it's just how far am I to my global optima. So that's the beautiful thing about convex problems is that they only have global minima. It might not necessarily be unique, but so it could be like a trapezoidal function with a flat basin, but nonetheless, so it's kind of like let's say you've isolated a solution down to lying on the unit circle, right? You'd have a phase ambiguity. So something like that, to where you could be anywhere on the unit circle, but it turns out for most applications that's a sufficient level of resolution. Yes, it's guaranteed. Yep, universally.
Excellent talk, Joshua. Thank you. So, do you think is there a loss of information going through categorically, basically formation of 3D matrix or tensor, or in other words, is there a gain to do a direct decomposition of tensor versus going to like a stacking format that?
Oh, yeah. So yeah, when you're dealing with tensor structures, right, there's SVD is uniquely defined on a two-dimensional signal. As soon as you got higher dimensional signals, it's number one, no longer uniquely defined, as well as it actually is technically intractable to compute the full decomposition in that sense. So you get into two realms. You can do what is a direct analog of the decompositions on tensor spaces. You can do things like Tucker-3, canacount, parafact, all those realms of decompositions. Those themselves are extremely computationally challenging even to do the decomposition. So that is one advantage of going to an unfolding space, is that you maintain both tractability and convexity on these. At the same time, you are collapsing them down, so you are potentially sacrificing, basically there might be, by representing things in a different way, a more efficient way to exploit the information. It's still a fairly open problem, I'd say, to look at what the trade-off between how good is a local solution in those non-convex problems versus the global solution in the convex unfolding space. And some groups have been looking into that, but I haven't seen anything which actually resolves that in, I'd say, a strong theoretical manner.
So when you're picking a local neighborhood, is that a general result that you pick a neighborhood that was roughly the same extent of all dimensions, that gives you the most bang for the buck?
Say that one more time.
So you mentioned that you have the tensor problem with MR. You have a very slab-shaped
Yep.
tensor space, and you pick local neighborhoods which are more equal, or basically the largest dimension is the smallest dimension of the data.
Yep.
Is that a general result that when you're doing these neighborhoods of picking a shape where everything's more or less equal in all dimensions?
So they don't have to be equal. You can make them isotropic. You can set up multi-scale versions of these. There's a whole spectrum of options in these cases. For most things that we deal with, some type of, when you do the local decompositions, they do hold extremely broadly. You can do full parameter sweeps over all the dimensions and marginalize out a lot of the effects and show that they do hold locally on a very large class of signals. And that's even by just assuming a single uniform block size. When you can start to consider multi-scale low-rank decompositions, you get even more power by having essentially adaptivity. So I would say you can't really prove it for every single signal out there, but you can prove it for a pretty large class of signals that you will encounter.
Is it good first guess?
I wouldn't call it a guess. It's definitely something which, there's actually strong theoretical rationale for doing it.
I'd like to thank Josh for speaking. It was great.